Hey guys, more talk about derivatives today. So we have three things we're going to talk about. The first thing we're going to talk about is the chain rule, which gives you a way to differentiate composite functions. The next thing we're going to talk about, let's flip over, is going to be derivatives of inverse trig functions, which are some pretty neat derivatives. And then we're going to talk about derivatives of exponential and logarithmic functions. So before we talk about the chain rule, I want to make sure that you guys can identify when you have a composite function, which would be the inner function. And I always think, instead of saying like g and f, I always think inner outer. So in this case, g of x is my inner function, and then f is my outer function. And so I kind of use these words throughout the video. So we have h of x, we have it defined for two different functions. We want to see which is the inner and which is the outer. Excuse me. So on this function right here, the first thing you need to remember is that sine squared x can be rewritten like this. Sine x all squared. This notation is just a little easier. If you were to stick it over here, you might think it was like this, sine of x squared, and then that would be something different. You get confused. So if we rewrite it like this, then we can see that this is my inner function, right? And then this piece is my outer function. So let's identify both of these. So for my inner function is g, right? G of x is going to be equal to sine x. And although that x isn't there, my outer function is squared. And we can't just throw a squared there without anything else. So my outer function is x squared. And if I were to make the composite f of g of x, I would end up with what I started with. Okay, let's take a look at the next example. So here my inner function is 4x plus 1, right? My outer function is e, not just e because that's a constant, but e raised to the x power, because, I'm plugging in 4x plus 1 for x when I'm creating a composite function. So here my inner function, which I'm calling g, is 4x plus 1. My outer function, which I'm calling f, is e to the x power. Getting a phone call. I'm sorry, I gotta pause this. Oh, sorry. Okay, I'm back. So we got the composite functions down. So now let's take a look at the chain rule. So this gives us a way to differentiate composite functions. So what we have here is we have, fix my pen all up. We have g of x again is our inner function, f is our outer function. So if we want to differentiate it, we differentiate f, the outer function. We leave g of x there. We don't mess with that. And then we multiply all of that by the derivative of the inside. This is the piece that you guys are going to forget. You'll remember to take the derivative of the outside and leave g there, but this is one of the most common mistakes, is just to leave out that the derivative of the inner function. I've also included the Leibniz notation for how this works. So if we want to differentiate dy dx when we have an inner and an outer, we take the derivative of y with respect to the inner function. That's what that says. I tell you, u over here is my g of x. That's my inner function. And then we multiply it by the derivative of the inner function with respect to x. Um, so it works both ways, either notation. So let's just look at some examples. So here we have my outer function is going to be cosine of x, or cosine u, and then I have all these different inner functions. I'm going to see what happens. So the first thing I'm going to do is I'm going to rewrite my function. I'll just call it, I guess, y, with the inner function plugged in. So this will be cosine of 9 minus x squared. So I'm going to do the derivative of the outer function and just leave the 9 minus x squared there. So the derivative of cosine is negative sine. Let's make some notation here. So y prime is going to be equal to negative sine of, not x, but 9 minus x squared. And then I want to multiply by the derivative of the inside. The derivative of 9 is just 0. And then the derivative of negative x squared is going to be negative 2x. And then I could clean it up a little bit. I could just kind of, get rid of those double negative signs. And I would end up with, let's see, y prime is going to be sine of 9 minus x squared times 2x. It's about as clean as you can get it. Okay, so now we have another one over here, although I think I'm running out of room. Now we want to look at the derivative of y equaling cosine of 1 over x. X to the negative 1 is 1 over x. So I want to find y prime. So the derivative of cosine is negative sine of 1 over x. And then I need to differentiate the inside, and so that's going to be negative 1 over x squared. That ends up being negative x to the negative 2, right? So you end up with negative 1 over x squared. I could clean up the double negatives and rewrite it, and it would end up looking like this. Y is equal to sine, like this, of 1 over x all over x squared. And I apologize, that's y prime. All right, so I think we got a good rhythm going here. You just have to make sure you're remembering. Multiply by the derivative of the inside. Can't forget about that peanut in your M&M, right? You could take a peanut M&M. The chocolate is your outer function. The peanut's your inner function. So let's try this one. So if we have u is equal to tangent x, then my y is going to be cosine of tangent x. So the derivative of my outside is negative sine y prime is equal to negative sine of tangent x times the derivative of the inside, which is secant squared x. Alright, that looks good. This is y prime. And there's not really much you can do to clean that up, so I'm just going to leave it the way it is. So it's not so bad. It's really important that you are able to identify inner and outer functions, especially when we start integrating and using u substitution. So I want to practice this just a couple more times. So here I have two functions multiplied together. So I'm going to have to use the product rule. But this one has this inner function. So I get to combine the product rule and the chain rule. So I want to find y prime. I'm going to start by doing the product rule. So I'm going to do the derivative of the first, which is 1, times the second, plus the derivative of the second. So let's think about this. It's going to be negative sine of 1 minus 3x. That's the derivative of the outside times the derivative of the inside. The derivative of 1 is just 0. The derivative of negative 3x is negative 3. And then I can't forget to multiply by the first part, right? Derivative of the first times the second plus the derivative of the second times the first. So I can't forget about that x right there. And now I do want to kind of clean this up a little. It looks pretty gross. So I have cosine of 1 minus 3x. I have two negative signs here, so I'm going to make those positive. So it's going to be plus 3x sine of 1 minus 3x. And I think that's perfectly cleaned up to me. Need a bigger highlighter. Maybe right too big. Okay, so now let's flip to the next page. So that was it for the chain rule. So you just need to get lots of practice, work lots of problems, maybe work a few odd ones where you can check your answer. It's always a good idea. So these inverse trig functions are some of the neatest derivatives, I think, because you start with a function that is periodic. They're all trig functions, and you end up with these rational, polynomial-esque derivatives. So I've just given you a list of all these. These would definitely be something that you would just need to memorize. There's no way to easily derive them. I would just, write that on your list. Okay, these are things that I need to memorize. So we'll kind of refer back to this list, but we're just going to play around and compute some derivatives. So the first one's real simple. I want to find the derivative at x equal 4 for y is secant inverse of x. So the first thing I want to do is find y prime. And if you look at your list, the derivative of secant inverse of x is going to be 1 over the absolute value of x times the square root of x squared minus 1. So that's real simple. You know, just pulled it from the formula sheet or from your memory, which is where it should be by tomorrow. And so now I want to evaluate it at 4. So this is just going to become 1 over the absolute value of 4 times the square root of 4 squared minus 1. And so this is going to be, it'll be 16 minus 1, so it'll be the square root of 15. So it becomes 1 over 4 times the square root of 15. And I'm okay with you leaving it like that. That's not so bad, huh? Really, the trick is just memorize, and I'd make some flashcards. It's like how I like to memorize things. So here's a little tricky one. I used a different notation just so you guys would remember that we have two notations for the inverse of trig functions. One is the trig function, you know, with the -1 power, and the other is arc sine, arc cosine, and so forth. And you could see both of these. So make sure that you remember that they mean the same thing. All right, so I have my y is arc sine of e to the x. So I'm going to take and I'm going to find y prime. And I have an inverse trig function and I have an inner function, right? So we're going to have to use the chain rule. This is my inner. And then this is my outer, right? So let's try this and see what happens. So the derivative of arc sine is 1 over the square root of 1 minus x squared. My x is not an x, though. It's an e to the x. So I'm going to take e to the x and I'm going to square it. Now I need to multiply by the derivative of the inside. So the derivative of the inside is just e to the x. So now I'm going to clean things up just a little bit. So I'm going to do y prime is equal to e to the x all over the square root of 1 minus e to the 2x. And that looks good to me. So once again, more practice. Memorize those inverse or derivatives of your inverse trig functions. And now let's talk about exponential and logarithmic. So this is kind of the last piece. We've learned how to take derivatives of all the different kinds of functions. We learned product, quotient, and so the last piece in just the methods of differentiation is to differentiate exponential and logarithmic functions. So we've already learned one, right? We learned the derivative of e to the x, because that's the coolest one. It is e to the x. Now, if you have just some constant, some exponential expression, where you have a constant raised to the x power, you cannot do the power rule here. So the derivative of this is not x times a to the x minus 1. The power rule only works when your exponent is fixed. It doesn't work when it's able to be changed, when it's a variable. So make sure you remember. I see that mistake a lot. Okay, but the derivative of your exponential function is ln of a times a to the x, which kind of makes sense because if I use the same rule up here, I'd get ln of e, which is 1 times e to the x, and that would just be e to the x. So it actually applies to everything. But that one's so neat, we tell you that way. Logarithmic, ln of x is a really neat derivative because the derivative of that is just 1 over x. If you have a different base, then you could either just use the change of base formula, change it to ln of x, or here's the formula for you. It's just the 1 over the natural log of the base times x. Excuse me. So let's try a couple of these. So here we have, want to find y prime for the ln of 9x squared minus 8. So I have an inner, I have an outer, and I'm going to have to use the chain rule. So I'm going to start by differentiating my outer function with respect to the inner function. So it's the derivative of ln is 1 over x. So this is going to be 1 over everything that's inside, which is 9x squared minus 8. And then I have to multiply by the derivative of my inner function. The derivative of 9x squared will be 18x. And then the derivative of negative 8 is just 0. So I end up, if I clean it up just a little bit, with y prime being 18x all over 9x squared minus 8. That's it. That's pretty easy, right? I wouldn't clean it up. I guess you could. No, you can't even divide everything by 2, so that's going to be as simple as it gets. All right, here's an exponential, so let's try this one. So I have an inner function, right? There's my inner. Here is my outer. And I want to find the derivative. So the derivative of my outer function, which is 11 to the x, is just the natural log of 11 times 11 to the x power. But mine isn't an x, it's a 2x minus 4. Oh, I kind of ran out of room there, sorry. And now I want to multiply, so I'm going to kind of put it down here, by the derivative of my inner function. The derivative of 2x is just 2. The derivative of negative 4 is 0, so this will be just times 2. And I'll clean it up for you a little bit. So I get 2 natural log of 11 times 11 to the 2x minus 4. I think y'all we're doing a great job. We're almost done. Okay, so last example. So I have a log base 3, so I'm going to have to use that rule for logs of different bases. And I have an inner function, right? So there's my inner. Here's my outer. So let's take and let's find the derivative of the outer. So this is going to be 1 over, right? And it's usually the natural log of the base times x. But my x is an x, it's sine t. So it's going to be the natural log of the base, which is 3, times x. My x is sine t. And then I want to multiply by the derivative of my inner function, which is going to be the derivative of sine, which is cosine t. And then I could clean this up a little. I could even go well enough to write that cosine t over sine t is cotangent t, right? So I'm going to write it like that. I'm going to write it as y prime is equal to cotangent of t all over ln of 3. All right, so next time we get to talk about related rates and all sorts of applications now that we've gotten through all the boring stuff. So y'all have fun working all these problems, and I will see you later.